Good afternoon. I can say that now. It's official. So welcome again to another in our SETI Talks Colloquium series. And we're delighted to have a very interesting talk today about the SOFIA program, the Stratospheric Observatory for Infrared Astronomy. So we hope to have a very engaging discussion, and we'll have some time for Q&A at the end of that. Before we launch into the talk and I introduce our speaker, I did want to give you all a reminder about what's happening next week at the colloquium. So for those of you who've been attending recently, this is old news, but for some of you it's not. So a week from today is an event in Silicon Valley called SV Gives, Silicon Valley Gives. So this is a day that is set aside by the nonprofit community to reach out to the Silicon Valley populace at large, and indeed I think it reaches up to San Francisco and beyond. But in any case, it's an opportunity for nonprofit organizations, including the SETI Institute, to sort of reach out to the community here, talk about the work that each of our organizations do, and try to raise some money. So we are making a major effort to do a fundraising campaign and participate in Silicon Valley Gives. There is a website, SV Gives, and I think it's Razoo is the platform, R-A-Z-O-O. And the SETI Institute already has a live website on that SV Gives, so people can start actually contributing and getting a head start on the day. But to have some fun with Silicon Valley Gives and the event itself, and to take advantage of the fact that it happens to fall on the same time as our colloquium, we're going to have a special colloquium event next Tuesday. We're going to have a panel session instead of our normal format of a speaker and single topic. We will have a single topic, but we will have hopefully 4 different opinions and perspectives on it. So we have 4 of our scientists from the SETI Institute, Dr. Natalie Cabral, who's the director of the Carl Sagan Center, Seth Shostak, who's our senior astronomer. He's also the host of Big Picture Science, that many of you are familiar with. We have Mark Showalter, who's one of our planetary scientists and most notable for his discovery of 2 of the moons of Pluto, Kerberos and Styx. And also Fergal Malali, who's been a speaker here before on exoplanets, and he's a wonderful speaker. So the 4 of them will be on a panel addressing the singular topic, when will we first find life beyond Earth? So each of them will share their perspectives on that question in a short introductory set of comments. Then we'll engage in some Q&A and discussion with the panel. And probably with 20 or so minutes to go, we'll have a microphone set up in the middle aisle here so that you can come down and ask questions and participate in the event. We'd like to have it be a lively event and get a lot of audience participation. So we will also on that day be honoring Bill Barucki, whom we all probably know by now as the well-known and beloved father of the Kepler telescope. So that'll be at the very beginning of the event. Also, Microsoft, who is one of the key sponsors of SV Gives, has been kind enough to offer to put on a lunch. So lunch will be served, and there'll be, some of you may have been here the last time that was done, but they typically set up in that aisleway near the top of the stairs. And there'll be a buffet lunch starting at 11:30. So you want to try to come and plan to get here early. And they will also very kindly allow us to have lunch here in the auditorium, so you can bring your lunch in here and get comfortably seated. We do want to kind of start as promptly as we can, because it's going to be, I think, a pretty full house, and it should be a fun event. So again, next week, that's SV Gives Day, and it's our panel session, 11:30 to start with the lunch here, and then 12 o'clock for the normal session. Again, the lunch is free, as the talks are free, and we're very appreciative of Microsoft's support. So, without further ado, let me introduce today's speaker, who is Dr. Pamela Marcum. And Pam began her research career with the study of white dwarf stars while an undergraduate at Florida Institute of Technology. She graduated there with a bachelor's and master's degree in space sciences and physics. Her research direction changed to extragalactic astronomy while in graduate school. And I thought when I read this, I thought, who can compete? How could a dwarf star compete with galactic astronomy? So little wonder that she changed course. In any case, she worked in graduate school on the near IR and optical properties of ring galaxies and galaxy groups, and also participated in the Hubble Space Telescope Wide Field and Planetary Camera 2 science definition team activities. She received her PhD from the University of Wisconsin-Madison and was a postdoc at the University of Virginia, where with fellow team members of the Ultraviolet Imaging Telescope at NASA Goddard, she worked on the first extensive UV imaging of local galaxies. Before joining NASA Ames in 2009, Pam worked for over a decade as a professor at the Department of Physics and Astronomy at Texas Christian University, I should know that, in Fort Worth, Texas. For 3 of those years, she was appointed at NASA headquarters, serving as the program scientist for the WISE and Kepler missions and managing the UV optical IR portfolio of the Research and Analysis Grants Program. As the SOFIA project scientist, Dr. Marcum's primary responsibilities are to assure the scientific integrity of the mission and to provide advice and guidance on the SOFIA program's Office on Scientific Issues. Her research interests are directed towards observational and theoretical studies of galaxy evolution. And as many of you may know, the SOFIA program is near and dear to our hearts at the SETI Institute. We run a program there called Airborne Astronomy Ambassadors, which is a program in which we put educators from middle and high school and also planetarium educators on the SOFIA missions, which you'll hear about it in great detail, and give them the opportunity to experience field science and field research, in person, and take the excitement and the passion of that experience back to their classrooms and their school districts. And this is a program that Edna DeVore, our director of education at the SETI Institute, and here in the audience today, she and her team manage that program, which again is one of our really important STEM education and education initiative programs at the Institute. So without further ado, let me turn it over to you, Pam, and thanks very much.
Thank you very much, Bill, for that nice introduction. And it's great to be here. And thank you, audience, for either postponing or doing away with your lunch hour today. One of the things you might have first noticed when you walked into the room was this really nice live model of SOFIA. I forget exactly what the scale number is, but it is in detail replicated very well with the actual airplane. It even comes with its own little telescope. So I urge you, if you didn't get a good chance to take a look at it, feel free to come up after the talk and you can pick it up or whatever. The wings do fall off, by the way, so I could play with you with that, but I won't. I'll warn you ahead of time. It's a little bit fragile in that sense, but feel free to take a look at it because I think it does give you a really good sense of just the scale, the size of the telescope, the size of the airplane. All right, well, as introduced, I am the NASA SOFIA project scientist. And what I'm going to be talking about today is sort of a general broad talk on what SOFIA is. It turns out that, at least according to some of my SOFIA contacts here, SOFIA talk hasn't been given here in quite some time. And so it seemed like a good time to introduce you or reintroduce you to a project that's literally right down the road. And if any of you are interested later in learning more details about the program, feel free to just get in your car and come over and visit with us. We'd be happy to have some guests and to discuss more about opportunities with SOFIA. All right, well, the first thing that I'd like to talk about is what exactly is SOFIA? You already have kind of an indication in the form of a model, but SOFIA stands for Stratospheric Observatory for Infrared Astronomy. It's one of the many acronyms in NASA. It is a Boeing 747 SP. For those of you who are avionics buffs, you probably know that the SP version of the 747 is a squattier version, made, I guess, to reduce air drag so it could go further. That essentially is what these models are known for, is being able to fly long flights. It has a 2.7 meter diameter telescope in the back. That's what you see in the back cavity here. 2.5 meters effective aperture because of the way that the optical path works. It flies above the region in the atmosphere where infrared light is absorbed, i.e. the stratosphere. And one of the many benefits of having an airplane that carries a telescope, as opposed to having the same telescope in space, is that you can service it. As the technology advances, you can update your detectors with state-of-the-art. As the science questions themselves evolve and change, you can retire instruments, put new instruments on that address those new science endeavors. It also has mobility. So this is perhaps the most unique aspect of SOFIA of all is its have telescope will travel capability. And you might not think that that's a big deal, but there are some advantages to that. And I'm going to show you one science highlight that takes advantage of that in a big way. The other advantage, speaking just from a ground-based observer, is that when you are observing in the southern hemisphere and then the northern hemisphere, say you're studying one set of objects, it's really nice to have consistency, the same platform, the same instrument setup, everything the same, so that you can get a consistent baseline of the thing that you're studying. And this observatory allows for that because it flies to the southern hemisphere as well. As I sort of alluded to earlier, one of the benefits of an airborne observatory is that you are able to maintain it. So if something breaks, you don't have to scramble to try to send astronauts up, even if that's possible. No, this thing comes home every night. And so whatever is broken can be fixed. And every now and then instruments, all of you, probably most of you are engineers or scientists, you kind of understand that game. And it's very nice to be able to tweak and get the best performance you can out of an instrument by virtue of the fact that you can pull it out, put it in your lab. SOFIA, as Bill mentioned, also has a very prominent role in education. I'm going to talk a little bit more about that once I show you the interior of the plane, so I'm going to hold off on any elaboration at that point for now. And also, one of the things that I've recently added to this bullet list in my talk is that the fact that SOFIA it's a platform. So those of you, and I don't know my audience, but those of you who are interested in other studies, for example, Earth atmospheric chemistry, radiation at altitude, airplane, human interfaces with the airplane. I mean, pretty much any realm that you have some interest in along those lines, SOFIA might be able to address. So we are looking for partnerships, interested in partnerships, I should say. And some of the ideas that have been put forth, for example, are little suitcase experiments. You put them up in the overhead bin. We still have those on the plane. That would just sit there passively and take measurements. Retrofitting, perhaps, some of the ports for atmospheric studies in a way that can't be done by some of the other planes that are dedicated for atmospheric sciences. So just to kind of get the creative juices flowing, if some of you happen to be working in that realm, we would invite you coming over and chatting with us sometime about what the opportunities are. One other possible venue of partnership would also be optimization. It's almost like a traveling salesman problem that we have. And let me just get into it a little bit, and then I'll just skip over it when I get to it in my talk. Stars rise in the east, they set in the west. You don't have any control over them. We have a hole in one side of the airplane, not the other. And so it's a optimization problem to figure out how to fly, how to make sure that you're pointed in the right direction to get the data on that particular object. Avoid all of the regions of airspace you're not allowed in, even NASA's not allowed in, and actually then to get back home and make it as efficient as you can make it. We don't want to be flying legs that we're not taking data on. And I will show you what I mean in a minute. So in other words, people who have computational skills, who Thank you very much. People who have computational skills who might be familiar with this kind of a problem, of course, we would welcome that kind of a conversation as well in partnering. All right, well, the background was a composite of all the flights that SOFIA has made, I think in the course of a year. This was made some time ago, so we should probably update it. But it makes a couple of points. First of all, we fly, each flight covers a wide path on the map here. So we fly out of Palmdale, but many of our flights takes us well past the Midwest. We once flew to Germany. That's what that one is all about. So we do most of our deployments is out of Palmdale, and we also fly over the Pacific as the science calls. But we also, once a year in the summertime, go down to the southern hemisphere where the stars are different, and fly out of Christchurch, New Zealand. And so what you're seeing there is a composite of all the flights that were conducted in one of the years that we had a deployment there. So here is an interior view, if you could see through the airplane. The telescope, when it's in operations, is fully exposed to the air. We fly with a hole in our airplane, and it flies beautifully. There's sort of like a garage door that slides over it upon takeoff and landing, but then it rolls back behind the aircraft when we're conducting observations. Obviously, you can't work back here. So the bulkhead, the pressurized bulkhead, allows for people, to live and breathe and work here. There are stations in here for telescope operations, for mission, the mission director. There's an area for the science teams to collect the data, and there are dedicated areas with computers set up for our educators program. And it doesn't just involve educators, it also involves reporters and other people who interface with the community, such as museum staff as well. So it's sort of a broad, the outreach component is somewhat broad. Now, of course, there's an upper deck in a 747, and the pilots are here, navigator, and if you get really lucky and talk nice to the mission director, he or she will occasionally allow you to get up there and sit behind the pilot and take off and landing. So that's really a cool thing to do if you ever get to fly. All right, so let's talk a little bit about the telescope itself. It is an odd telescope. It's not a telescope probably like you've ever seen before. It has lots of motion in this direction, but very limited motion in this direction. But you have to have both motions in order to keep up with the stars that typically make arcs across the sky as they rise and set. So most of this motion is provided by the plane's heading itself. So each leg of a flight is pointed, it's done so that the telescope can point to one particular object, and then it changes heading, and then it's on another target, it changes heading, and then it's on another target. So when you look at a flight path for a given night, it kind of looks like a drunken pilot. But it's a very purposeful, and as I elaborated on earlier, it's actually quite an optimization problem, traveling salesperson kind of a problem. Now, this is how the optical path works. So now we're kind of looking more at a sort of a schematic. And what you're seeing here is the primary mirror kind of edge on. And what you're going to see is the light coming in from the top. So the infrared light gets split off by a tertiary mirror, and it goes into the science instrument itself. So the science instrument is on the person-friendly half of the plane, so it can be somewhat serviced during flight, minimally, and of course operated. And so I'll show you some pictures of what those instruments look like from the interior of the cabin. One other thing I want to point out, though, is that this telescope's 17 tons. It's a lot of telescope, and the weight primarily rests on a spherical ball bearing, which floats on a thin layer of oil. to help kind of suspend it, and that's how it's able to maintain its position, its orientation during an observation. There are what I call shock absorbers. There's probably a technical word for it, but it kind of looks like a shock absorber in a car that surround in 3 dimensions this ball to keep it from any serious buffeting by the airplane itself. And then, of course, there are gyros, which also help keep it pointed in the same direction. When you're flying on the airplane and you look backwards, and I should probably describe the story. Hold that thought. Let me get back to it in just a minute. Let me finish the optical path. So the tertiary mirror splits the light. Part of it, the infrared part, goes to the infrared instrument, and then the other piece, the visible piece, goes to the guide camera, which really is a misnomer if you have ever conducted observations with other telescopes. It really doesn't. The guide camera isn't constantly keeping the telescope locked in because it's kind of locked in already by virtue of the fact it's sort of floating freely. What it does is just ensure that we are pointed in the right direction and then to alert if there are some issues where we get out of sync. All right, one of the things that is important to understand is the answer to the question, why all of this? Why don't you just take that telescope, put it on a tall mountain somewhere, and call it a done deal? And the reason we don't do that is because water vapor in the Earth's atmosphere is really bad for infrared astronomy. Basically, those water molecules and other greenhouse gases absorb the infrared and don't allow the photons to make it even down to the ground, even at really high, the peaks of the highest mountains. This is a demonstration of what the difference is, the contrast of what you see with SOFIA versus that mountaintop observatory. So this is, say Mauna Kea. Blue is bad. Where you see blue means for those wavelengths, so this is wavelength versus the transmission. For the patches where you see blue, you can't see at all at that wavelength from the ground. And what you can see at the ground-based level are these little windows, these little gaps of wavelength. But clearly there are large swaths of the infrared to sub-millimeter wavelength space that are completely unavailable. But in SOFIA, pretty much every single wavelength across this range can be observed at, with the exception of maybe right here and right here. Yes, we still do have some water lines and other lines, molecular lines that intrude. We have techniques to eliminate that from the data. So the point of this plot is basically suddenly the plus or minus 50, 60 microns from 100 microns wavelength range is suddenly now available. And if you don't remember anything else about this talk, remember this. SOFIA is the only game in town for these wavelengths. There are no other observatories out there that can access this wavelength, this swath of wavelength range. You might say, well, what about JWST? JWST is going to be a wonderful observatory. It is highly synergetic with SOFIA activities, and its wavelength range, I probably should put it on here. I'm just guessing. It would be about like that on this plot. So it's more of a near to mid-infrared observatory. You might say, what about Spitzer, which is an infrared observatory that's already in orbit? Well, Spitzer, some time ago, went into, it lost its cryogen. And so the 2 longest filters are no longer operable, so it can operate in the 2 nearest filters. So it's operating kind of in this range. And it does imaging, not spectroscopy. You might say, well, what about Herschel, if you're familiar with astronomy, recent astronomical observatories? Herschel was a 4-meter telescope, considerably larger than this. It operated in this wavelength regime, and it was really awesome. But after about 4.5 years, it ran out of cryogen. So it was not serviceable, and so it was decommissioned. So SOFIA is really the only access to these wavelengths that the astronomical community has right now. All right, so we talked about wavelength accessibility. What do we use to study those wavelengths? Currently, SOFIA has, it depends on how you count them, but about seven instruments. Some of them do imaging. Some of them do somewhat crude spectroscopy, the ability to sort of slice up the light into a rainbow. And then some of them are extraordinarily high spectral resolution. This plot kind of gives you this is eye candy, by the way, and now I'm going to show this towards the end of the talk. So spectral resolution, how finely are you able to distinguish one wavelength from another, and wavelength. And on top of this plot, you can see overlaid are different instruments. And then on top of that are sort of the areas of science that you might be able to address in that parameter space. So again, like I said, this is mostly eye candy, and we'll get back to it in a minute. What I did want to get back to, and I left this dangling a little while ago, was the interior view of the observatory. Now, the plane looks better now. It kind of looked a little rough around the edges because we hadn't gone into what we call a D-check, which happened 2 years ago, where they put really nice panels. It looks like a nice commercial airline now, but this kind of looked more like that grunge laboratory look for a while. And but that's okay, it worked. It just wasn't appealing. What you're seeing here is the cabin side of the telescope. Really, you're not seeing the telescope. You're seeing the little hole that bores through that spherical bearing upon which the weight of the telescope rests, that the light gets piped through. And then the light comes out here, and then you can put whatever instrument you wish to analyze the light. And there's these really hefty bolts that bolt on the instrument. This happens to be great, and I can't remember the acronym, what it stands for at the moment, but it is our longest wavelength in the far infrared German-supplied instrument. I should mention, SOFIA is a partnership. 80% NASA, 20% DLR, the German space agency. All right, so now what you see here is they're getting ready to install it. These tend to be pretty heavy. There's a reinforced floor actually to help out with this particular maneuver, and that's really all it takes. You just roll the thing up, you put the bolts on, and then you're pretty much, after a couple of connectivity tests, you're ready to go. So we can switch out an instrument in about 36 hours if need be. This is during flight what it kind of looks like. It doesn't look anything like an airplane. It looks like an observatory with a lot of people in it. We typically fly between 20 and 35 people on any given flight, depending on the size of the science instrument team that's visiting. And so what you see here is huddled over here are the science team members themselves. This is the PI of the instrument that happens to be mounted on the telescope at the moment. And then over here, this person is the telescope operator. So he's the actual person who controls whether the telescope moves. And then, of course, what you're not seeing, like here, would be where the educators would be, where the consoles are. But, all bets are off once you're given the you can get up signal. The educators are right in there mingling with the science team, as they should. That's part of the experience, right? Okay, so why infrared? This is kind of just a little plot to sort of on a almost kind of a not something we know on a daily basis per se, but some of you have probably been in military, thermal glasses or whatever. That's infrared. So this happens to be sort of mid-infrared, between 8 and 10 microns. So we're not talking about the extraordinarily long wavelengths that I mentioned before that SOFIA also covers. But just at a glance, you kind of see, what thermal infrared is all about, right? It maps temperatures, differences in temperature. The cute little cuddly dog turns into something in your nightmares, and it's because of where the heat is actually coming out. The cold lizard looks cold against the warm, glowing hand. You can't see anything visually in the dark, but with the infrared, you can actually make out the thermal radiation coming off of the ostrich. Now, of course, in astronomy, the same is true. Things look differently depending on what wavelength you look at. So this is a picture, well-known picture, and probably a lot of you have perhaps even taken your own pictures of this nebula. It's called the Horsehead Nebula, and if you turn your head sideways, you can kind of make out what looks like a horse. This is a region where there's a lot of new stars being made. It's a region that's very dense. There's clouds, not like the clouds out there outside right now, but clouds of gas and dust in interstellar space, and these are the places where new stars are formed. And what you see here is kind of nothing. It's dark. It's very dark. You see, the glow from some nebulosity, a couple of stars, but what you're not seeing is what astronomers are interested in. This is a very dusty cloud, and so it's blocking a lot of the light from the stars embedded in that cloud. So when you move to near-infrared wavelengths, suddenly most of that nebulosity goes away, and you can actually see the stars that were behind the clouds. And the reason for that is that at longer wavelengths, the longer wavelength light is less affected by the dust obscuration. So it's able to zip right past those dust grains and get to our telescope. So I often say it's sort of like X-ray vision, but I hesitate to say that because X-rays is a totally different kind of radiation. So, but it does sort of give you the ability to look down deep inside of a star-forming region, which is exactly what you want to do if you want to understand how those things are made. And then at even longer wavelengths, so now we're talking like 100 microns, you actually see the glow from those little dust grains themselves that were causing all the problem visually. So 3 different pictures at 3 different wavelengths, and they beautifully provide a complete picture of the physical processes in this part of the sky. Now, in addition to being able to tell temperature differences, being able to see through the dust and see the dust grains themselves and analyze the dust grains, how big they are, what they're made out of, all of that you can get from infrared observations. In addition to all that great stuff, there's more. Wait, there's more. Many lines in the infrared come from molecular species. And if we want to understand basic chemistry, how does water get formed in space such that it then gets deposited on planets like Earth, some very life-sustaining ingredient like water? Turns out it's a very complicated process, actually. It starts out with 2 hydrogen atoms having to make a chemical bond. But in space, imagine it's like billiard balls, right? So what you actually need are dust grains for those hydrogen atoms to deposit themselves on, get rid of a lot of that kinetic energy, and then kind of migrate along the grain and find each other. So there's all kinds of very complicated factors involved in allowing even water to be formed. And so some of the studies that have been conducted with SOFIA try to follow and understand the chemical pathways that form water, and other species as well. It turns out there's some interesting questions about, for example, sulfur and oxygen that people are using SOFIA to better understand. Okay, so speaking of spectral lines, and this isn't of a molecule here, this is of a carbon atom. Going back to our friend, the Horsehead Nebula, this is a recent picture, and we'll get back to this in more detail later if I have time, of this area mapped out at one particular spectral feature caused by singly ionized carbon at 158 microns. And you'll see a little movie going on. I'll just let that be a teaser, and I'll get back to that later, what that's all about. But this provides insight into where those carbon atoms are and how fast they're moving. I'll give you that. We'll get into it a little more later. Okay, so what have we learned through the use of SOFIA? So I'm just going to go through right now and just give you a bunch of science highlights, and I'll probably go through it quickly so I can have time for questions. One of the big topics that people are studying is in trying to understand the formation, that process that led to our own existence, the solar system, our sun. What we like to do is to conduct experiments that are provided for us by nature of star formation in extreme environments or environments that constrain a parameter in some way so that we can see, oh, if you tweak this, because this particular star forming region has that tweaked, oh, okay, so that's the outcome of that. So what if you add more dust? So, and so we'll study this region. So by looking at a full range of different environments, one can perhaps be able to fully flesh out and understand the physical process of star formation, which, so why is star formation so hard? Think about it. Just at a top level, and there's more factors here, but So you have this big molecular cloud, dust and gas. It's cold. Under its own mass, it starts to pull itself in under gravity. But as it compresses, what happens to gas when you compress it? It starts to get hot, and then it wants to push out. So you have those two forces that are opposing each other, and there's equations that tell you when gravity will win, what the density has to be such that gravity wins. But then there's all kinds of other factors. You know, this molecular cloud isn't all out there all by itself in a nice, clean, sterile environment. No, it's perhaps in an environment where there's tidal forces trying to rip it apart, or shear forces trying to disassemble it. And then there's many other factors. Does it have a lot of dust in it? Does it have, is there a real hot, ionizing source nearby that's trying to disrupt it? So there's all these factors that weigh into dictating whether or not a star is actually produced in that cloud. So in this particular example, what has been found is that the Galactic Center, the center of our own Milky Way galaxy, has a profound amount of star formation. And not just star formation like our sun, no. It's doing star formation in a big way. Very, very massive stars, almost pushing the limit of how big a star could be without sort of blowing itself up before it became a star. So the highest number of massive young stars with initial masses that are pretty much pushing the limit of how massive a star can be, there's nowhere else in the galaxy with this number as in the Galactic Center. But the Galactic Center is actually an extreme environment. There's a big supermassive black hole in the middle, and affiliated with that is a really strong radiation field. There's tidal forces. There's all of that. Magnetic field, strong magnetic field, so things that could tend to disrupt. So how is it that these stars are there? So one idea is, do they form in situ? And then we'd really like to understand the physics of how that happened. And or are the extreme environment factors what made the big stars? And you don't get the big stars elsewhere in a more mild environment. Or did these stars form elsewhere and then migrate in to where we see them today? All right, so there were two investigations that were done. One was more of an imaging investigation conducted by Forecast, one of our near-infrared instruments. And what they saw were these knots. By the way, this is the highest spatial resolution. This is the crispest picture of the Galactic Center that you will have ever seen up to this point. And they were able to resolve these little knots and study them in detail. How hot are they? What is, well, let me not get ahead of myself. So that's just a pretty picture. What they were able to do, and the results were also provided by the GREAT instrument at the far infrared, conducting slightly different investigations but coming to the same conclusion, is when they looked at those little knots, which you can barely see in this beautiful picture here, when they analyzed those knots in detail, what they found was they were transient features. They were too hot and not massive enough to hold themselves together for a time scale that would allow star formation to occur. So you can draw whatever conclusion you might draw from that. It kind of sounds like maybe, I don't know, in situ star formation, at least in this molecular ring, might be ruled out. I don't think they actually said that in the paper, but that's my inference from reading the papers. All right, so another kind of cool thing they did was they looked at these two identical twins. So these are, first of all, these are really rare stars. There's not that many of them in the whole galaxy. And they're called luminous blue variables. And it turns out in this part of the galaxy, near the Galactic Center, there's actually two of them very close together. And they were born at the same time, and we know that because the luminous blue variables, because they are so bright and so energetic, they actually, by radiation pressure, blow out a cocoon around them. And so what you're seeing is that cocoon. And the cocoon, for both of them, is roughly the same radius, which implies that they're roughly the same age. But they're so different in appearance, and the question was why? Well, it turns out after some analysis of the temperature profile seen in these cocoons, that the investigators concluded that this heating didn't occur from within. It actually occurred from outside. This is outside heating of this cocoon caused by another very massive star assembly right here, whose radiation field was actually ionizing and heating up the cocoon. If you look really carefully, you see another kind of cool thing. Note that this is spherical, roughly, and there's a distinct flattening on this side of the cocoon. That's the radiation pressure from this other stellar star cluster, distorting that cluster. So the takeaway message for this slide is you might start out the same, but your local environment actually can drive the appearance and perhaps even the ultimate fate of these two stars. All right, so boy, we got some heavy-duty physics coming up here. Let me see how fast I can get through it. One of the things that SOFIA has also been used for in a really novel way is to look at the earliest stages of star formation. So if you're going to try to understand the processes that lead to star formation, all the factors that I described earlier, what you'd really like to do is catch it at the earliest embryonic stage, right? And then follow that process by looking at different evolutionary stages in the galaxy all the way through. Infrared allows you to do that because, again, you can see all the way down to the dense core of these clouds, so that's one thing in our favor. But one of the problems that has plagued observers for a long time is being able to understand what you're looking at. Is this cloud actually collapsing or is it not collapsing? So one diagnostic they try to use is the fact that if the cloud is collapsing, the side that is closest to you will be going away from you. It's called a redshift. It's a Doppler effect. So you probably heard trains or a siren go by and the pitch kind of changes. Right? I'm kind of making it up, but it kind of changes pitch. Light does the same thing through the Doppler effect. And so it's redshifted relative to where that spectral wavelength would be if you were to observe that particular molecule or atom in the laboratory. Now, if there's outflow, then you'll see that side coming towards you. So it's a simple matter of looking at the Doppler shift of a spectral feature and saying, is it coming towards me or away from me? Not so easy. Ground-based observatories have tried to conduct this work for a long time. And here what you see is a spectral feature of a molecule where the game is to try to see which side is a little dimmer. You look for asymmetries. The dimmer side is deduced to be the side that's further away. I don't know about you. I'm not an expert in this field, but it's really darn hard for me to see asymmetry in that line. Well, in comes SOFIA, and it provides a very robust measurement. So what it looked at in this case was the ammonia molecule. Ammonia, in this case, is a strong absorber. You only get absorption on this side. You can't see absorption here because there's nothing to absorb against. The core provides the bright light source, the light bulb that you're seeing the absorption against. So the gas, the molecules of ammonia here produce an absorption feature. And then the question is it redshifted or blue shifted? So the fact that it's absorption is great because it then says you're just looking at this side. And then all you have to say is this wavelength, like I said, redshifted or blue shifted? In this case, it was redshifted, going away. So it meant that particular cloud was actually collapsing. So they were able to catch the star formation process in its earliest phases. All right, so this technique was then applied a year later to a whole bunch of other clouds, as you might expect. Once you get a tool, you want to try everything. And what they found was roughly half of the clouds that they looked at were actually infalling clouds, which again will lead, once you identify these clouds, then you can go in and do other studies with them as well. All right, so shifting slightly in gears, one other technique, again using a chemical composite, sort of like a molecule, in this case H2D+, where the D is deuterium. What they did was they looked at the ortho to para ratio. So what is ortho? Ortho, very quickly, is where the proton in the two hydrogen atoms are spinning in the same way, as shown here. Para, as you might guess, is where they're spinning in the opposite direction. And then it's simply a matter of measuring this, how much of this you have and how much of this you have, but we're gonna show you that in a very demonstrative way here. So the idea is that over time, ortho, because it's at a higher energy level, actually decays down to para. It converts to para over time. And ortho and para have their own special signature, so you're able to analyze and measure how much ortho and para there are by looking at the two different wavelengths that you can measure these. So over time, and you're going to see the ortho disappearing, the spectral line dropping, and this getting bigger, and then more pink dots as time goes on. Over time, the ortho turns into para in a very well understood manner. So it provides a clock. So then all you have to measure is ortho and para, and then bam, you can figure out how old that molecular cloud is. So here is a model. So the yellow line is a really young cloud. And then just look at one particular temperature, because there is some temperature dependence. Just look vertically. So then it gets a little older. The orthopara drops a little lower, and it gets older. It drops a little lower, and then all the way to 5 million years old, the oldest in this set of models, where the ortho has pretty much completely changed to para. And then you kind of get the idea of what we can do here. So you go out and you actually measure the ortho and para for real. So you're seeing the actual data here. This was the data provided by SOFIA. This was data supplied by a ground-based submillimeter telescope called APEX. So they simply measured those lines, ratioed them, and bam, it constrained it within this box. And so they got an answer of more than 1 million years old. Well, this is a puzzle, because if you just take simple physics and allow gravity to act, it should have taken 1/10 of that amount of time. So what is holding the collapse up against gravity? That's really the answer. And I'll leave that to a follow-up question if you want to. Well, we'll explore it a little bit towards the end of my slides. I think in the interest of time, I'm going to skip this one, although it's very interesting, and go to a very visually cool science result. So mostly SOFIA dwells in the infrared, but sometimes it does do visual observations, and this is where the mobility comes into play. Twice now, most recently this past year, there was a Pluto occultation where Pluto passes in front of a background star, makes that star blink out for just a moment, and the way it blinks out provides insight into Pluto's atmosphere, if it has an atmosphere. And it turns out that sometimes it has an atmosphere and sometimes it might not, because Pluto is in a very weird orbit, taking it very far away from the sun and then a little bit closer, and the variance in the distance from the sun could cause, at some point as it's going further and further away, the whole atmosphere in Pluto just completely freeze out and collapse. So that's one of the ideas, or one of the questions that they had when they conducted this. So a lot going on here. You're seeing Pluto actually doing its thing. So it's about to occult. You can see the fuzzy atmosphere just starting. This is what the light curve looks like. If you stare at the star, you can actually see that it's blinked out. And then it comes back as Pluto emerges out of the other side. And then what's really happening is a shadow's being cast, right? And SOFIA, talk about flight planning. This thing is going, 100 times faster, than the plane can go. So it had to all be preordained so that it flew right underneath the cloud at the right moment. And what we wanted was to catch it in the dead center, because there's some interesting things that happen in the center of the shadow. Did you know there's light in the center of the shadow? As nature would have it, one of the occultations was only 2 weeks before the New Horizons flyby. So it allowed a really unique way to remote sense the atmosphere and then compare the results to boots on the ground, which will allow SOFIA to track Pluto for a long, long time. I think this is my last science highlight, so let me just quickly, I know I've gone over my time a little bit. One of the big questions in cosmology, and SOFIA isn't generally thought of as a cosmological tool, is where did the dust come from? I've already talked about dust a lot. Dust is important. It helps make molecules. It's where the meeting spot is for the molecules to get together. But in the very early universe, we needed dust to build things like planets, to make molecules. So where did the dust come from? For a long time, people said, it's got to be supernova. That's the thing that happens first. It's got to be these massive explosions of these big stars that were the first things to form. The problem with that is some time ago, using the Chandra X-ray Observatory, it was discovered that the bubbles left behind, so-called supernova remnants, are filled with really hot gas. There's actually, the shock goes out in the explosion, and then it kind of piles up stuff, and then the energy actually bounces back. And it's pretty energetic. So the thought was, gosh, supernova would be a great candidate for the factories of dust, but I wonder if it just gets all shattered and destroyed in this rebound. Well, so this was one of the questions that SOFIA was used to address. So we looked at a supernova remnant, and lo and behold, we found the signature of radiation from dust grains. So that's what the yellow is. The background is the X-ray radiation coming from this supernova remnant. Okay, so the best is yet to come. This is the plot that I've shown you before. And so you might be saying, hopefully you're asking the question, well, what did slow down that collapse, that gravity collapse? One thought is magnetic fields, which no one wants to talk about because it's hard physics. But we'll be able now to do observations to test the theory of how relevant magnetic fields are to star formation using a brand new instrument called HAWK+. So it does polarization. It's an indirect way to get at the magnetic field lines in a region. This was the original HAWK array. It started out as the first generation, but because SOFIA is awesome in allowing upgrades and new technologies to be taken advantage of, HAWK got upgraded, now HAWK+, to the larger array that you see there, plus polarimetric capability was added. Another instrument that shows the upgradability is, you've heard about GREAT earlier. It used to be 1 pixel, so right there. And if you wanted to map something, you literally had to stamp it out like that. Well, now we have a multiple pixel array where the mapping goes much faster. Now let's go back to the Horsehead Nebula. You already saw this before, and now I'm going to describe a little bit more about what's going on here. This is a composite of, if you stack all that, that's what you get here. Every instant that you see here, what you're seeing is all of those cloud blobs moving at a specific speed. And then the next step in that video is the clouds moving at a slightly different speed. So it's what we call a data cube, and the velocity you can see scanning across here. The upgrade, which is the upgraded version of GREAT, was able to provide this amazing data. Right, I think I'm going to skip this. Things that we can do to understand the solar system, if you want me to go back after the talk is over, I'd be happy to describe to you. But SOFIA is not just, I've only sampled, cherry-picked some of the highlights of SOFIA, but SOFIA can also help people understand planet formation theory by some really clever techniques that I just blasted through. So I think I'm going to stop it there. Maybe we have a question or two.
Thank you. So I think you've demonstrated one of the challenges of talking about a platform instead of a single science question, because there's so much science that can be done with one platform. Where do you start and where do you stop? But
that's right.
You covered a lot of ground, so
yes,
thank you so much.
Absolutely.
So we have time for a few questions. If there are some questions in the audience, I'm sure Pamela will be able to address those.
So how many days a year do you fly the aircraft, and then how many observing hours do you get?
We fly, on average, about 3 nights a week. It accumulates to about 900 hours, and these are research hours a year. And each flight is from go to stop is 10 hours, but we probably get about 8.5 hours of actual research time, because we have to allow for time to passively cool the telescope and to get at altitude. And then, of course, the descent, we don't do observations.
Thank you. You had a slide you skipped over at the end about water. Could you talk about that, please?
Yeah. I was hoping someone would ask about that. I'll try to do this real quick. One of the applications of XEs, which is the really high spectral resolution instrument in the mid-infrared. So this overlaps JWST capabilities, but JWST doesn't get at this high spectral resolution, I might add, is understanding protoplanetary disks. So this is a schematic of that. And kind of the holy grail is to understand where this water snow line is, because it has relevance in formation models. It turns out to be kind of a roadblock for stuff that's trying to radially migrate in, and it kind of gets clogged up there, and it allows time for cores to form that might turn into Earths or Jupiters or whatever. And so how do you, these are really tiny in the sky. You can't possibly image them, but what you can do is spectroscopically infer from them. So using simple physics, Kepler's law, what you do is you look at different spectral features of, say, ice and water and maybe water vapor, just to cover the bases there. And you'll notice, if everything was working right, if the ice is all coming from sort of one place and then the water is coming from another place, they'll have different shapes. Those lines will have different shapes. The ones that are closer in, because they're rotating faster, will be broader, and the ones that are further out will be narrower. And by measuring the widths and also whether or not they have a double horn profile, which also provides insight into the dynamics, you can put it all together and map where that ice came from, how far away from the star it was, just by basic orbital mechanics. And so this is one technique you apply to a bunch of different planetary disks to see where the snow line is, and then see if that result is consistent with planet formation models. So they kind of feed onto each other. Yeah. Thanks for asking.
Thank you. A simple question to give you a little bit more understanding. I'm not in the field of planetary science, but has SOFIA contributed to a radical shift in how at the center of the universe or center of the galaxy, of our galaxy, stars are formed? Is there any new ideas, or is there confirmation of existing models?
I would say to date, the operations has not gone on for a significant amount of time at this point. And we do hope for a big headliner on NBC News, nightly news in the near future. But I would say what SOFIA, and I've sort of given you some examples of where I think SOFIA has made some serious contributions. Resolved some unanswered questions, made some unexpected surprise findings as well, like the really old cloud. I don't know if that answers your question or not. And there's other examples of where a field was advanced by SOFIA findings. And if you'd like to talk a little bit more, if I could point you to some more other papers, which I didn't cover in the talk today because of lack of time, I'd be happy to do that. But one place to go is our webpage, which not only allows you to have access to our papers, but it provides sort of a synopsis of some of the science highlights, many more than I've covered today. So I'm not sure, maybe we could talk afterwards if I haven't really addressed what your question is. Yeah.
I'm just curious of this aircraft and how it relates to the aircraft that's sitting up here at NASA Ames. And is this a successor aircraft? That's number one. And number two, why are you in Palmdale and not up here?
Ooh, that's a loaded question. First, what you're referring to is the KAO, the Kuiper Observatory, and it was the predecessor of this airplane, a completely different airplane. The telescope was in the front, and I don't know a whole lot about it because a little bit before my time. But it had like a 20-year mission, I believe, and very, very successful in what it did. But certainly this is a much larger, much more capable observatory. So why is it in Palmdale? At the time that the decision was made to put it in Palmdale, it was argued that NASA Armstrong, that was their niche, building one-of-a-kind planes, testing them, flying them. And actually, it was the right answer. They got it done, and I can tell you that when this thing is flying, you don't even know that the door is up. So I think that's all I can say about that now. We can talk later.
My question is why there aren't more such observatories, and is the lack of them because of the big problem of the open door and the aerodynamic forces at work there?
If I understand what you're asking, why aren't there more SOFIAs?
Yeah.
It's expensive. I think probably in a nutshell, that would be an answer, yeah. There are some suborbital projects. They're very focused on one particular science question done by scientific balloons. but they have some limitations as well. But they're way cheaper. So that's sort of being done. So I lied a little bit when I said absolutely no observations are being conducted in those wavelengths. Some, science balloons are conducting. They get much higher. They get much higher, yes. So they get even more out of the atmosphere and have less problems with the lines. Yeah.
Thank you, Pam, for a wonderful discussion. But I wanted to ask about exoplanets and planetary disks and things like that. What does SOFIA do in that respect? Does it look at planetary disks, or does it look at some of the transits that we see for some of the larger planets?
Yeah, that's a good question, Bill. Thanks for asking about exoplanets. SOFIA has been used to conduct a couple of transit observations, and the findings haven't come out in the paper yet. So I can't really comment a whole lot on those, on the end result, whether it was successful or not. I know that one of the observations was to use some of the narrowband filters that was available in the mid-infrared camera that we have, and to try to hone in on some key molecular signatures during the transit. It was kind of a high-risk observation, and again, we haven't seen that published yet, so we're still kind of waiting to see that, and it would be really exciting if they were able to actually make that work. It would really open up a lot of potential, I think, for future such observations if this one observation kind of worked. I think that the story is perhaps more positive for protoplanetary disks, though, and that is because of the extremely high spectral resolution capabilities that we have within our instrument suite to do kind of like what I showed a minute ago, to really be able to kinematically resolve spectral features and then sort of trace them back and develop a chemical profile within a protoplanetary disk. One other slide that I think I omitted from my talk was the ability, because of the high angular resolution at, say, 20, 30 microns, to actually be able, for nearby, a limited number of nearby protoplanetary disks, actually detect where it's been swept out by an invisible planet. So I know that one particular observation was focused on that question.
Okay, one more question.
Thank you. How do I ask this? A couple of years back, there was talk of scrapping the whole thing.
I knew that's where you were going.
That's why I try to be careful with my words. You've shown us, very exciting talk, thank you very much. You've shown us that the instrument, the observatory, has accomplished quite a lot in what is a very short time, right?
Yes.
Do you have any feel from headquarters or from the senior reviews as to whether the science you've accomplished up to this point has yet put us in a position where the future of the observatory is stable?
That's what keeps me up at night, to be perfectly honest, that question. And I think that's probably a good thing to be on guard. We've done SOFIA, not me, we. SOFIA has done extraordinary science. And I appreciate that you appreciate that. Perhaps what we as a team have not been so good at is tooting our horn, quite frankly, and kind of getting the word out there that SOFIA is breaking into areas that can't be done by any other instrument and addressing really fundamental questions. I won't speculate as to whether that message has reverberated into the headquarters domain, or even if that's where who knows where it needs to be shouted at. We don't know what directions are sort of putting up challenges, right? But all we can do is keep on doing good science and keep focused on that, because that's, at the end of the day, what matters anyway, and let the rest play out. I guess that's sort of the survival, philosophy. I'm sorry?
It's all about peer-reviewed papers.
Absolutely, absolutely.
Headlines helped. How many people had ever heard of LIGO before the gravity waves were detected? Just a few. But anyway, so thank you again very much. Please thank our speaker.
Thank you very much.
And I do want to present you with the coveted SETI Talk Speakers mug.
Oh
which,
my gosh.
Again, these are
I will cherish
treasured.
them. Thank
Yes,
you very
please.
much.
Treat it with care. But thank you for that talk, and keep up the wonderful science. It's even ground-based observatories, rarely make headlines, but the science being done is profound, and certainly true with SOFIA, and we're very happy of our education program as well.
Yes, and one thing I didn't expound upon, I meant to, and sorry about that, was that, SETI has been an amazing partner, and we really, really cherish, the AAA program. We know that it's gone in some different directions lately, but I am very optimistic that, it will continue to thrive as it has before. It's really made a lot of impact.
Yes, well, we just started a new 3-year cycle, which we're very happy about. To your point, headquarters has changed some of the parameters they want around metrics and measurement of effectiveness, but we're working on those issues and delighted to be partnered.
Thank you.
So great. Thank you again so much. Thanks, everybody. Hope to see you all next week.